Okay, so I think we'll get started since it's 8:40. So I'd like to introduce our next team, which is team number 25, who is the Green Grocer. So very exciting cover slide. Take it away.
Good morning, everybody. We are MKTP Corporation, and we are here to talk to you about Green Grocer, our anaerobic digestion system used to process supermarket food waste. My name is Kim, and I'm the experimental lead. This is Mike, our technical lead, Priya, our marketing and research lead, and Tyler, our project manager and business lead.
So just a little bit of background about our topic and the problem that we're trying to solve. So the United States food waste is a big problem in the U.S. About 40% of the food in the U.S. isn't consumed and is actually wasted. And this equates to 63 million metric tons of food waste, which is a problem, not just because a lot of food is getting wasted, but also when the food breaks down and is sitting in landfills, it produces a methane gas, and that is really harmful to the environment. So to tackle this problem, we wanted to look mainly at supermarkets because they have a very large amount of food waste. There are about 38,000 supermarkets in the United States, and they generate about 8 million metric tons of food waste. So there's a lot of food waste, that this is a problem. And not only that, this is also a growing problem. As you can see here, there's about 6% growth in the waste management market, and the food waste management market is going to reach about $35 billion by 2027. So this is a growing problem that we want to address. So we're going to talk about our solution in the next few slides, but just at a high level, we're planning on taking that organic food waste that is being produced in supermarkets and converting it into a slurry, and then it will be put into an anaerobic digester where it will be broken down by microorganisms and other bacteria. And then this is going to produce a biogas, which will be converted into electricity and heat through a combined heat and power unit. And then we'll have another byproduct of digestate, which is basically fertilizer that can be used in agriculture.
So just to talk more about the methane that Priya mentioned, methane emissions by source, about 20% of all methane that's emitted in the U.S. is emitted at landfills. So we think that this anaerobic digestion process will really help to kind of drive down some of that methane that's emitted at landfills. The biogas that we're creating is a known renewable source of energy. We'll be doing this at a very local level. And even the digestate that we're producing as a byproduct can be used by supermarkets as fertilizer. They can donate it to farms, things like that. So we're really looking to tackle that methane emission problem. In addition to that, we think that anaerobic digestion will also carry lots of cost benefits. We'll talk about this in detail a little bit later, but everything from reduced electricity costs to disposal costs for getting rid of food waste, and even the possibility for tax credits, given that we're in kind of this new sustainable environment where there's lots of new legislation that's being introduced all the time. So again, our mission here, just to recap, is to seek to create an alternative energy product. It's going to be used by local supermarkets, and it's going to do two things. It's going to be sustainable, and it's going to help drive down operating costs for individual supermarkets themselves.
Okay, now we're going to go a bit into the technical side of the Green Grocer. Start off with a bit of proof of concept. So anaerobic digestion is a technology that's been widely researched and widely used. Research has shown 4 key reactions inside the process. There's hydrolysis, acetogenesis, and methanogenesis. And this is a process that has been widely used in industry for electricity generation, such as in municipal waste facilities, warehouses, cafeterias, and even some breweries are getting involved with this technology, such as Magic Cat up in Vermont.
It's a little finicky.
It's a little slow.
You could maybe exit and then just click on the next slide.
So this is a detailed depiction of our P&ID. We basically have 5 units. We have a grinder, a bioreactor, a biogas storage tank, a digestate storage tank, and a CHP, or a combined heat and power unit. We have, along with that, 6 process control systems for each of them, with the exception of the reactor, which has 2, and 3 safety alarm systems, which are highlighted in red. Just to reiterate our process, we have depackaged food waste entering the grinder along with a certain amount of water and catalyst. and that is being ground up and sent to the bioreactor where it stays for 10 days, or a 10-day mean cell retention time, and it is broken down into both biogas and then the remaining digestate slurry. So the biogas gets sent to the biogas storage tank and then eventually to the CHP where it produces electricity for the supermarkets and heat that goes back into the bioreactor to maintain mesophilic conditions at 37 degrees Celsius. The remaining parts of the bioreactor or the digestate slurry get sent to the digestate storage tank, which then gets separated over the 10-day period, and the liquid water gets sent back into the grinder for recycling, and the solid part gets used as a fertilizer in agriculture. Oh no. And so these are our mass and energy balances that were sort of previously described in the previous slide. We had to make certain assumptions to reach these numerical values. So for the first one, the grinder, we had to use a certain amount of water to achieve a 20% total solids by volume, as well as a certain amount of catalyst to achieve a certain concentration based off of our decision to use silica gel as our catalyst. That gets sent to the bioreactor, which produces biogas, and 55% of that ends up being methane, with the remaining being carbon dioxide. And that's a pretty standard breakdown for anaerobic digestion in terms of food waste itself. The CHP produces around 50% heat, 40% electricity, and 10% is wasted, and that is just simply based off of our specifications of our unit. And then the digestate storage tank is just a separation of the aforementioned solids and liquids.
Okay, so back to the first step of the process. This is going to be the grinder, and depackaged food waste is going to be put into the grinder, broken down into a sludge that has about 70% moisture content and 30% total solids. And as Kim was saying, we're looking for an idealized total solids percentage of 20%. So after the grinder process, we'll be adding more water to bring up the moisture content to 80% and keep the total solids at 20%.
And the process control system for this is a moisture control system, and this is basically used to detect the moisture content of the slurry being fed to the reactor, or in turn the total solids, to ensure a certain level of viscosity as well for ease of flow.
Okay. The next step in the process is our reactor, which is anaerobic. It's kept around 37 degrees Celsius and continuously stirred. And this has a mean cell retention time of 10 days, which means that as the food is fed in on day one, it sits in the digester for about 10 days, enough time for the naturally occurring microorganisms to decompose the volatile solids, produce biogas, which then flows out through the top into the storage tank. And then after 10 days, that digestate is pumped down to the digestate storage tank. And using our calculation, the mass balances and the EPA's density for food waste, we came up with a volume for 5,500 liters that should account for the 10-day MCRT.
And there are two process control systems for the reactor. They're both composition control systems that detect the biogas composition and the digestate slurry composition. And this is just to ensure the progress is going accordingly for the 10-day MCRT period.
Okay, the next part of the process, we have the biogas storage tank, which we calculated at 50,000 liters, and this is to account for a little over 2 days storage for the biogas, though we do assume the supermarkets are going to be using the biogas daily to help offset their electricity costs. And the biogas from there then gets fed into the CHP unit, which converts biogas's energy into 50% heat, 40% into electricity, and then 10% of that energy is lost in the process.
And there is a process control system for the biogas storage unit that is basically a pressure control system. It monitors the flow of biogas as well as ensures that overpressurization wouldn't occur, because that would definitely be a safety concern. And there is also a temperature control system for the CHP unit, and this is to ensure that the CHP unit is functioning properly and to also make sure that the heat is being supplied back to the bioreactor.
Okay, and then going back from the reactor, the digestate goes into the digestate storage container, which, using the remaining solids and water inside the reactor, calculated a volume of 2,000 liters, and this will also count to hold for a 10-day period of the digestate. And this digestate is a sludge which has a higher moisture content than the initial sludge, as a lot of the volatile solids break off and convert to biogas, so you're left with a lower total solids percent in this feed. Though the digestate can be very useful for enhancing soil characteristics, so we intend to sell this to the local farmers in the area.
And lastly, we have a process control system for this. It is a level control system to ensure that overflow does not occur of the tank.
Okay. And in regard to process safety for the greengrocer, there's not a whole lot of negative things that can occur with this. The one thing that is potential is methane leak, as we are combusting methane and it is a combustible gas, so we intend to give the operators handheld methane detectors just to keep a watch for any of the leaks, and also provide them with proper PPE, gloves, glasses, hard hat, and steel-toe boots. And there are also a couple alarms on the system. The type 2 alarm on the moisture control system that's on the grinder, a type 4 alarm pressure control that's on the pressure control system, the inlet to the biogas storage tank, and a low temperature interlock on the CHP unit. And we also have to take into account some of the regulations regarding the greengrocer. The air pollution regulations, as CO2 is being emitted from the CHP unit, that's something we're going to need to take into consideration. Additionally, we are dealing with solid waste, so we may have to deal with the local enforcement agencies to oversee our solid waste activities. And additionally, there is permitting that may come into play, as consolidated permitting for dairy anaerobic digesters is a thing in California, and we may need a similar permitting process for organic digesters. However, this is a new implementation of anaerobic digestion, so the regulations and what we will have to abide by are not so set in stone at the moment.
So now it's time to talk about our experimental portion of our capstone. As you have probably gotten the idea, anaerobic digestion is somewhat of a slow process. It can even take up to 40 days in terms of mean cell retention time. So we thought in order to improve our production rate and to just overall optimize the process that we would look into catalytic options to achieve what we have now, which is a 10-day MCRT period, and even lower depending on the sort of results that we continue to achieve. So right now in literature, there's very little research being done for catalysts for anaerobic digestion. We were only able to find silica gel that is being tested for cow waste, and alumina and iron oxide that is being tested for fruit and vegetable waste. And so our idea was to consolidate this into one experiment that basically used the same food feedstock with all three catalysts being tested amongst each other. So I made a video that sort of demonstrates this process as opposed to me explaining it. You can see it, and just to bear in mind, we used pressure as a means of detecting how much biogas is being produced.
Fish or Sci are borrowed from other labs with the exception of the feedstock that was bought from Whole Foods. The PPE used was pretty standard, just nitrile gloves, a lab coat, and lab glasses, and as always, closed-toed shoes and covered skin. Each of the soups was poured into an overall batch and mixed together in order to ensure homogeneous distributions amongst all serum bottles. A graduated cylinder was used to measure out each of the 150 ml volumes, with funnels for pouring in all circumstances to avoid any countertop spills. Paper towels were distributed to maintain an environment that was as clean as possible.
Hope you guys are enjoying the music. Hard choice.
Each of the bottles was labeled according to whether or not they were the controls, silica, alumina, or iron oxide using tape and a marker. Ordinarily, I would deposit the catalyst into the bottles first and label after that, but I wanted to switch steps for this experiment because I noticed that I was cleaning the glassware that both iron oxide and alumina would clump to the bottom of their respective bottles. I wanted to try a different procedure. You have to be careful with iron oxide because it stains and is hard to come off. We had intentions of using a crimp seal, but the compatibility of the seal with the bottles we ordered was falsely advertised, and we had to improvise how to maintain an anaerobic environment. I headed over to True Value to purchase airtight sealant, which ended up working great, but forced us to only rely on single point measurements as opposed to taking measurements all throughout the 5-day period. The bottles were left in the shaker incubator for 5 full days, at the end of which a pressure was taken for each. This was done using a 15 psi pressure gauge attached to a thin metal needle that is inserted at an angle into each rubber stopper. The angle is important so that the needle makes contact with the environment within the bottle. And that's a wrap, folks. Thanks for watching.
Hope you guys enjoyed that. A little video intermission. Yeah, so that's basically how I ran 3 separate experiments with different feedstocks. The first of which was a tomato slurry, the second of which was cream of mushroom soup, and the third of which was butternut squash soup, all from Whole Foods. So as you can see, the pressures are pretty variable in terms of the feedstocks themselves, and that is really just a direct correlation between the viscosity, which was highest with cream of mushroom soup, and it produced the lowest pressure, but the tomato slurry had the least viscosity, so it was the most easily flowing, and it ended up producing the highest pressure. But I want you to disregard that for now and just to focus on the differences between the catalysts and their respective controls for each experiment. So on average, for the first 2 experiments, the range between the controls and the catalysts were around 3 psi, and that was pretty fruitful for us because we were able to proceed with choosing a catalyst for greengrocer because we were seeing pretty distinct results in terms of the difference between the control and the catalysts. The third experiment, which was the one with the video, ended up producing inconclusive results because there was 6 psi pretty much generated all throughout, with the exception of iron oxide, which had a slightly higher pressure at 6.5, but that was a little surprising because it was the poorest performing catalyst for the first 2 experiments previously. So silica and alumina were determined to be our best contenders for the first 2 experiments, producing the highest pressures. But we ultimately chose silica because it is a more environmentally friendly catalyst for being fed back into the agriculture. Due to basically its use as a fertilizer and an insecticide in some circumstances, so it yields like a safer cradle to grave process because we do have digestate being fed back into the environment. And also it just has an overall lower bulk cost, so it seemed appropriate to choose with a little under a $200 price per batch with shipping. And so we do have experimental recommendations, though. If we had the luxury of time, we would have tried to strive for reproducibility. So we would have tried to test each feedstock 2 more times to ensure statistical results as well, because we can't exactly fully rely on these results. Obviously, we're going to continue to explore them in our R&D process throughout year 1, but right now, we have to go with what we found. In addition, it would be really helpful to test the particle sizes of each catalyst. We were only granted these catalysts based off of availability in certain labs. I kind of had to hunt to find them. So if we had more time, we would be able to test different particle sizes and see what results could happen from that. In addition, I mentioned in the video, we originally were trying to go with crimp seals, but they weren't fitting properly in spite of the way things were being advertised, so we had to settle on glue sealant. And this was great and it worked, but the problem with that is that you can only take 1 pressure measurement, and ultimately it kind of doesn't stick a second time. So if we had crimp seals, we'd be able to have multiple point measurements, and that would generate a trend line, which would give us more information about how the catalysts are acting, and it would also give us more information about how that third experiment ran with butternut squash soup, which seemed to give like even results, but there might have been other things going on that we missed. In addition, if we had a solid content meter, we could shoot for a 20% total solids value each time for each feedstock, and that would eliminate the variability of pressures for each experiment.
So next we're going to talk about marketing and how we are going to market the green grocer to supermarkets and tell them how it's going to be beneficial to them. So first we started out with a market evaluation to see if we actually have a need and if our solution would actually be a viable solution in today's market. So some of the key takeaways from that was the urgency and the market size. So today there's a push for green energy and clean energy. So there are a lot of industries that are moving towards this, and so it would be easy to market this to supermarkets because they can also work to provide that clean energy. And then the second was the market size. There are a lot of supermarkets in the U.S. As we had mentioned before, there are about 38,000 in the U.S., so there's a large market of customers that we can reach out to. Some of the things that weren't so great for us were pricing potential and upsell potential. Because we are creating the green grocer for supermarkets, they're not making a ton of money, so we can't really price this super high. So we just have to keep that in mind. We also did a market evaluation for landfills and compost, which are the two methods being used today for disposal, and we saw that they were in the low 60s, and so our solution is a good solution that can be brought to market today. And so here are some of the competitors that we have. So Angle and Gray is a composting facility in California, and so basically they just take all the supermarket waste and then they use it for their composting unit, and then they sell their compost to different agricultures. And so it's not very beneficial for supermarkets because they have to pay for transportation costs, so there's a lot of labor involved with that as well, and they don't really reap any benefits from that as well. And then the second, we have Divert Inc., which is actually a company that established a large-scale anaerobic digestion unit in Massachusetts. And so this is a great facility for supermarkets to give their waste to, but again, there is a transportation cost, and supermarkets really have no incentive to actually give their waste to the large-scale anaerobic digester when they could just go with their landfill or compost or whatever they normally do to dispose of their waste. And then finally, we have Impact Bioenergy, which is our biggest competitor. So this is our biggest competitor because they make small-scale anaerobic digestion units, and they make them for restaurants and cafeterias. So they're not really seeing as much waste as we are seeing from the supermarkets. And on top of that, we will be incorporating our proprietary blend of catalysts, which Kim talked about a little bit before. And so that will make our product and our solution much better for them. So to highlight our need, we actually contacted supermarkets around the U.S. We contacted 4 major supermarket chains, and we talked to them to see how much food waste they were getting, to see if we actually have enough food waste to actually run an anaerobic digester on. And so we found from them that there's about 200 pounds of food waste wasted per week from each supermarket, so there's a ton of food waste, and Mike and Kim did their calculations based on that. Also, when we were talking to supermarkets, we wanted to gauge interest, so we talked about our solution, and we wanted to see how they reacted, and the companies were all for it. We actually had one lady who asked us if this was already on the market and if she could buy it. So we had a lot of great turnout, and we know that this is a need, and our customers are real, so this kind of just helps our solution. Another thing that we want to point out is that supermarkets have such a low such a low profit margin. So every dollar that they save is equivalent to $59 of sales revenue. So this is a lot. If we can save them a little bit, we're saving them a lot in the long run. So the green grocer will benefit supermarkets in 3 main areas. So the first area is electricity. So we will be saving them and cutting down their electricity costs, which are equivalent to about $144,000 of sales. So this is a ton of money that they can potentially save by just implementing this system. The second is disposal. So supermarkets have a large disposal cost, and that includes tipping, hauling, labor. So we can reduce this up to $20,000 per supermarket. So this again is another large savings for them. As well as the third point, which is the planet. So each individual supermarket will be able to have a direct impact on the environment. About 13% of landfill space is just supermarket waste. So each supermarket store can make a direct impact in reducing the methane gas emissions.
Okay, so now we're going to talk about our business and how we're going to operate and what our goals are. So first off, we talked about this earlier, but our facility is going to be located in Orange County, California. We did kind of have a viability factor ranking that we did in order to determine if this was going to be a good location for us. We do have some pretty good benefits. First off, market access. We have about 900 supermarkets directly located in Orange County. Lots of shoppers, specifically lots of green shoppers who are very health conscious and very sustainability oriented. Also, logistics and incentives were pretty high. We're in a very heavily populated area with very high density and lots of different industries. And also incentives. California is a hotbed for all sorts of sustainability efforts. So we know that we'd be able to have partnerships with the state as well as with the county for our initiative. There are some downfalls. Facilities is pretty much the big one. Very expensive to rent and lease facilities in Southern California, as well as vacancies, which are at an all-time low, so again, increasing those prices for us. As well as labor and regulatory, given the relatively high minimum wage and kind of the uncharted territory related to permitting for our process. So us at MKTP plan to operate one facility. It's going to be 20,000 square feet. We're going to have roughly 10 employees or so, including us, initially for the first year. We do plan on having lean inventory. We're going to practice just-in-time manufacturing to keep our inventory low. We're also going to make sure we work with our suppliers as well. And we're going to really kind of have a culture that is focused on continuous improvement, continuous flow to kind of really maximize the facility that we're using. This is a first-year timeline for us. We do plan on purchasing all of our materials and our capitals in January, and then we're going to go into a period of R&D and startup again to make sure that our experimental results are kind of cohesive on a larger scale. And then we do plan on commercial manufacturing to begin in August. So as a result of that, so our supply chain, which I mentioned briefly on the last slide, us at MKTP plan on being the manufacturer, distributor, and retailer. So we'll be working directly with our Tier 1 suppliers to give us our raw materials where we can take to assemble greengrocer, and we're selling directly to customers. So we think by kind of owning those two different pieces of the supply chain, we'll be able to control costs on our end and have great relationships with our suppliers and with our customers. This is a look at our projected manufacturing output. Again, with our first year, we plan on outputting about 20 units, and that's based on our 5-day cycle time. So we think with our current employee capacity, we'll be able to output 1 unit every 5 days roughly, or once every business week. And then after that, starting in 2020, we do plan on doubling that, just given the amount of time over the year we have to market as well as to manufacture. And then we anticipate roughly 20% growth kind of after that, and that's based upon just the size of our initial market in Orange County as well as possible expansions throughout California and throughout the United States. Taking a look at our capital cost estimates, our largest capital cost is our warehouse. We initially planned to lease the warehouse, and then after looking at our long-term projections, we thought it would definitely be a better idea for us to purchase. It would be a great capital investment for our company, owning real estate in a pretty hot market. So we thought that would be a good decision to make that change. Also, one of the higher items here is our transportation equipment. Given that we are going to be the distributor selling directly to the customer, we are going to need that equipment to be able to transport our unit from our manufacturing facility to supermarkets in the area. And this is a breakout of our operating costs. At $850,000 a year, roughly 73% is devoted towards salary and labor for our employees. That's relatively high percentage versus other companies in terms of operating costs. But again, because we plan on having only about 1 or 2 units of inventory in-house, those usually incur high operating costs. So we think that by keeping the inventory low, we're okay to have kind of a higher breakout of salary and labor. And you can see utilities is roughly about 10%, given that we are kind of an assembly facility for our greengrocer. Talking about our revenue streams, our primary revenue stream is obviously going to be from the sale of greengrocer. We have it priced at $100,000. This gives us about $60,000 in profit, given it costs us about $40,000 to $45,000 or so for manufacturing and equipment and things related to that. We also are going to recommend that each supermarket that purchases Green Grocer does servicing, which is 4 times every year at $500 a visit, and that would include servicing, cleaning, and kind of regular maintenance, as well as this supplemental mix, which would include the catalyst that Kim was talking about, as well as water that would be added every time food is put into the unit. So we think that while Green Grocer is going to kind of be our biggest revenue stream, we're going to see lots of sustained revenue coming in as more units are put online and are serviced at about $500 a visit. So with that, taking a look at our revenue and income, it's important to note that with that first year, given that we aren't manufacturing too many units and we have lots of capital and operating costs in that first year, we are kind of in the red in terms of net income. But then we do see, again, that sustained growth, and that all of these factors include our depreciation of our tangible assets as well as our amortization of our property that we'll be owning. So we came up with about 30% growth rate over a period of 5 years, which we think is pretty steady, and a payback period of about 5.6 years. So just to recap some financial takeaways, we're looking at about an 18% return on investment, our discounted cash flow that we calculated over that 5-year period, which is pretty variable given it is a startup time for us, is about $4 million. But we do think that we have pretty sound growth and would be, a good investment for investors that are willing to take part in this sustainability effort.
In an age of sustainability and green economic practices, there's been no better time for a commercial anaerobic digester. Go green grocer.
Thank you. We do have some acknowledgements.
Before we wrap up, we wanted to have some acknowledgements. So we want to thank our mentor, Peter, for all of his help throughout the semester and for showing up today. I know it was really early. Dr. Webster and Professor Roy, who's, I guess, downstairs. Professor Bencherif and Dr. Miller for allowing us to use their lab space, as well as Mabu Bey, Professor Bencherif's grad student, and Rob Egan for developing a part for my experiment, and Professor Willie for just supporting the whole endeavor.
So with that, we will take any questions you might have. Thank you. Thank you.
Questions?
Yep.
How did you guys come up with the idea for how to conduct the experiment?
So that's a good question. I actually worked at Greenlight Biosciences. At some point we had an overlap, David, and at one point we were working with methanogenic bacteria, so we had to use serum bottles to sort of seed them, and I kind of modeled my experiment off of that, because we had to, that's why I wanted the crimp seals, because I knew like the whole process, but like things didn't work out. So I basically kind of stole that process and modeled it off of this one. So.
Yes?
But you guys have come up with the 10-day mean cell retention time, and what's the implication of that to the grocery store? Do they have to store the food while they're waiting for that process to finish? And is that taking up space that they could otherwise put fresh product in?
So to that, 10-day MCRT and 15-day is what we kept seeing across in literature. And though the 15-day does produce a bit more biogas, with the 10-day you can get more feedstock into the reactor over a period of time, therefore producing a bit more biogas in the long term. So that was kind of the choice to go with the 10-day, and also it helps with the reactor size because it allows us to keep a smaller reactor. And if we had the 15-day, we'd have another 5 days to account for, so it'd probably be about 50% larger reactor in that sense. And to the food storage, ideally they'll be feeding it every day into the reactor, so there shouldn't be too much holding on inside facility. But if there is any holding, it should be something we imagine that they have in process, as they're not going to be pushing off their food waste daily to the landfills as they're currently doing. So we envision that also not being too big of an issue.
Yes.
What do you guys think is going to be your biggest challenge for your company in your first year?
So I think our biggest thing would be marketing the first year, because there's so many supermarkets. We actually have to go out to the supermarkets and talk with managers. And a lot of these decisions come on corporate level, so we're going to have to go up to the corporate level and talk to them and prove to them why this is beneficial for them to implement in their individual grocery stores. So I think that's going to be our largest setback the first year will be marketing. But I think once we get that, once we market to a few supermarkets, it'll kind of generate a stream, and more supermarkets will see this being implemented and will want to jump on the bag.
Yeah, and even the fact that like supermarkets, like it's a pretty antiquated industry. Like, you know, aside from like maybe computer technology, not much has really changed over the last, 30, 40 years in supermarkets. So we think that kind of talking to them and really selling them on this product, we definitely think it is feasible and they'll be more than willing to. But it's just those initial conversations, and I think that's why we decided on the location in Orange County in California. That's definitely like a hotbed for these activities. Yes?
All right, I have a few questions. First is, do the people running these systems require any sort of training to operate this equipment, or just like you're going to have your high school supermarket grocery boy running your anaerobic digester? Is that feasible?
It's a great question. Do you want to?
Well, I mean, we'd want them to have some sort of qualifications, but they wouldn't necessarily have to have like a degree, like in chemical engineering, to be able to operate it. And also, we haven't like quite written the SOP that would be required for an operator to run it. And the reason for that would be we'd want to have like a system set up first, so that we would be able to realize all of the kinks that we're missing, because we can like generate an SOP now, but like there are all sorts of like things that we would definitely leave out because we aren't running through it ourselves. So yeah.
Yeah, and to add to that point, we'll also be going in every 4 months or every 3 months to service the unit. So we'll be able to talk with the operators and see if they are using it correctly, if anything needs to be changed. So we will have that customer feedback in there as well.
I have a quick question.
Yes.
So as far as like implementing these for the supermarkets to basically make it worth their while, what's the payback period for them in terms of just like energy and transportation cost savings? And if you are selling them to the corporate level, it seems like they would probably be rolled out sort of in bulk, and would you have the capacity to manufacture them?
Yeah, that's definitely a lot. So the first thing in terms of transportation and electricity costs, we do know on average for that 2,000 pounds of food waste every week, the amount that they would be able to save, which equates to about $2,500 every year. So we know that if on average they're generating that food waste, that's what they'll be able to save directly in electricity costs. So that would obviously be factored into their operating expenses kind of as a reduction in that sense. In terms of transportation, we found in our research that it's very variable. So located in Orange County or in Los Angeles at a place where they're definitely going to have to truck it out, then they'll have very expensive hauling costs, which could be upwards of like $20,000 a year, which is obviously very high. So just completely eliminating that out of the question totally would definitely be a major like immediate savings. But we do think it is kind of like on a per supermarket level in terms of kind of their payback period. We do think it would be definitely a long-term investment for them to be able to have this. And also that sustainability piece that's not necessarily like a direct cost savings to them, but just the fact that they're able to help the environment by reducing methane emissions, we think would be an appealing option. And then the second part was, I forget.
I don't know if this is true, but I'm just hypothesizing that if you're selling these at a corporate level,
right.
If you sell to Whole Foods, they're going to want 50 of them for all of their grocery stores in the county.
Yes.
But would you have the capacity to do
Right,
that?
yeah, no. So we think that our strategy right now, while we don't have a lot of employees, our manufacturing philosophy and using this just-in-time manufacturing and making sure that we have continuous flow and our cycle times for manufacturing are, again, that 5-day, that we'll be able to output a lot. It is going to depend on our marketing strategy, and if we wind up where we have a company like Whole Foods that's very interested in implementing this at like 20% of their stores, for example, we are going to have to increase our hiring to be able to meet that demand, but we think that our manufacturing strategy will allow us to scale up and to be able to kind of have quick flow of our product through our facility so that it's not just sitting there in a pile or we don't have tons of raw materials.
So adding to that point as well, we're going under the assumption that large corporations aren't going to want to implement like 30 units just up front. They're going to want to try it out with one location first. And so for that first year, we'll be able to output that one unit per week.
Excellent. So maybe I can ask the last question. I think I only have a minute. But I thought it was great.
Thank
I
you.
think not only taking advantage of the fact that you can do experiments
Yes.
to try to prove your ideas and learn a lot from those experiments, right? You could probably see, you could have a PhD thesis looking at the catalyst.
Kim, that's a great idea, Kim. Have you thought about that?
I mean, it's worth considering.
But you did a great job, and I actually loved the quantification of the marketing and the location too. You don't see that a lot, where you actually put numbers into, and as engineers we like numbers, but you put numbers into your thought process,
Right.
which was wonderful. The one, maybe the only question I'll ask is the 20%, the desire to have 20% solids that you mentioned. So I wonder if you could talk a little bit about, you know, the advantages and disadvantages of that. You know, why do you want that? And then also, it's a balance between that and some other things. So if you could go through that thought process.
So to that, we came across a paper that was testing out the 10% total solids, 15% total solids, and 20% total solids in our mesophilic anaerobic digestion range, which is what ours is. And the 20% seemed to yield higher biogas production time and time again. And additionally, I think behind that is with higher total solids, there's higher volatile solids inside the mixture. And those are the solids that are going to be decomposed by the microbacteria and be converted into biogas. So if you increase the total solids percentage up a bit, then you're going to have more of the volatile solids to be reacting and thus generating more biogas.
Excellent. So those are all the advantages. How about one you know, what problems would that pose for your process?
I feel like with that, it may be could potentially clog some of the pipes if we have too much solids going in there. It may be a bit too sludgy, and we may have to water it down at some point if we do run into issues with not being able to clear the pipes consistently, or if gunk's constantly building up around the edges. So that is something we would have to consider going forward.
And definitely, like, also from the literature, like, it was kind of interesting, and you guys can speak to this more, but a lot of the literature is more like farm waste and things like that. So for us to kind of be able to do this on a supermarket scale where we have all different types of organic waste is definitely, you know, a challenge where we were relying a lot on, like, studies that, like, just looked at tomatoes or something like that. So it was kind of interesting.
Yeah, so the source,
Right.
can make a difference in the percent that you
Absolutely.
actually want. But definitely the processing problems that could ensue could be significant, right?
Yeah.
Excellent. Thank you, guys.
Thank you.
That was great.
Thanks.